Those of you on Zoom, can you just check to make sure I can hear you real quick? Just say something.
Can you hear us?
Yep. All right. I'll turn you up a little bit. All right. That way, if you need to say something, I got it. Those of you on Zoom. Whoops. All right. Got this rolling, and we are. Where's my other remote? Man, that holiday break was nice. I could tell him relaxed up here. Come on. Oh. All right. So I want to talk about Newton's Earth law. Grab a couple of markers here. You on that, Jules? Nice. We talked about this before. It's the famous action reaction. And it's probably the most misunderstood. What page did I say we are? Page 88 approximately. Something like that. Yeah, somewhere around page 88, depending which version of the book you have. I'm going to say it this way. Let's do it this way. Very good. All right. All right. There's a lot hidden in this one phrase, this calculation here. The force that one exerts on two is equal and opposite the force that two exerts on one. Now, a fundamental thing here, notice if we call this the action and this the reaction, I want to point out something crucial. This one acts on two. This one acts on one. If you can get this down, most of the rest will be easy. Most important here is to realize the action and the reaction are on different objects. You can't have an action-reaction pair acting on a single object. Okay? Now, when I was a kid, I played this game called Clue, and I know that that's probably not that popular now, but it was like Colonel Mustard in the conservatory with the lead pipe killed Mr. Whatever. Well, I think of these action-reaction pairs a little bit like a sentence. So let me give you an example. Let's say I have an action here. Okay, and let's say the action is Earth pulls down on block with gravitational force. All right. So let's say that is the action. If you're trying to get a reaction and you have this.
Mr. Jorston,
Yes.
can you let Maria in?
What's that?
Can you let Maria in?
Oh, Jules, I thought you had that. Oh, I didn't make the co-host. Okay, say something next time, will you? Sorry about that. Thank you for saying something. My bad. Sorry, I thought I'd make Jules co-host, but I had not yet, so that's my bad. All right. Sorry about that. Okay, so, and thanks for speaking up on Zoom. Appreciate it. Okay, so again, let's say we can write an action in this sentence form. Okay. The reaction, the trick is we look at these key things right here and look at this sentence, or right, this equation is a sentence. All you have to do is flip 1 and 2, right? So let's start with there, block. Now, what is going to be the opposite of pulling down? Pulling up. On what? on Earth, what type of force? Also gravitation. And if you have this down, that's it. And the common thing is people want to always believe that normal forces and gravitational forces are action-reaction pairs, and that's just not true. All right. Something that is always true is you always have two objects involved, and the order of the objects gets switched. The direction gets switched. The type of force remains the same. That's action-reaction pairs. Questions on that? What do you think? Not too bad? And so if you could, I just really want to emphasize this. This is usually on a test, sometimes a test and a final. A lot of times they'll put a question about something like this on there and they'll say, suppose the action force is this, blah, 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 and I'll write a sentence. And I'll see if you remember how to flip the sentence. It's been on a large number of tests I've given. So, all right, so far so good. Turns out understanding this is crucial for us to understand friction, systems, and a number of other concepts. Let's take a look in here. I'm looking on page 88. Look at the bottom in bold. 3 bullet points in a row. 3 bullet points in a row saying the normal force and weight are never an action-reaction pair. And yet on exam 1, about 30% of the time, students still screw it up. I don't know what else I can do to tell you. That's just never true. So yeah, I'll give you an example. I'll show you something else. This is what drives me crazy. So imagine you have a block on an inclined plane. What is one force that acts on this block? Anybody? Gravity, which way?
Down.
Here we got mg. What is another force?
Normal.
Normal force. All right, which way? Perpendicular. What? To the plane, yeah, good. Notice if you have an incline, in this case, you can clearly see they're not equal and opposite, right? Now, maybe there's even other forces. You could argue maybe there's friction or something else, or maybe this block is accelerating. But I'm just trying to emphasize clearly the only time normal force and mg are equal and opposite is a block on a flat surface with acceleration equal to 0. In that case, the normal force happens to be equal and opposite, but that doesn't mean it's an action-reaction pair because it's not the same type of force. They're on the same object. That just doesn't work. It's not an action-reaction pair. Enough said on that. I'll let you know after test 2 what percent of the class screws it up. All right. Hopefully it's not you. I'm warning you, it's going to be there somewhere. All right. Enough said on that. All right. On page 89, there's a whole bunch of problems that you can practice with that. So I'm going to let you look at those at home, and you should practice enough of them so that you get a feeling for how to write the sentence for each force. But in the meantime, let's maybe look at a physical example over here. I need a volunteer that has low mass. Relative to me, so pretty much anybody in the class. Yeah. Let's do this. Let me zoom out. Oh, Dom, you're in there. Hey, Dom, can I get you to rotate that table back like this? We're going this way, right here. All right. Somebody got to sit on this hovercraft. Want to do it? You remember how to do it, right?
Yeah.
All right. So we're going to do a classic example of this one. Now, so we have to get centered on here. We can do 2 cases of this. So Zoom, is it showing up, Jules? Yeah. Thanks. So what you're going to do is sit on there, and we're going to push as hard as we can out on this cardboard tube. Right. And when that happens, we should push away from each other. I'm just going to point out here. Do you agree I have more mass than this guy by a significant amount? I don't know. Well, do you care to tell me how much you weigh?
Like 140.
Oh, shit. So I'm like 240, close to 250. All right, so Now think about this. I have approximate, let's see, he's 150 and I'm 250. What is that? 5/3 or something, at least 50% more mass, right? So in this case, we're gonna sit down on here and we're gonna push as hard as we can. This object right here is pretty stiff, but it has negligible mass compared to us. So I want you to think of this as basically a massless object. What we're gonna do is we're gonna sit and we're gonna push as hard as we can and not grip it. Just let this fall after we push. So when we do this, should our motion be the same? Should it be different? What do you think will happen if we both push as hard as we can? Who's gonna push harder? What's that? Yes, exactly. It's the same, right? Because Newton's third law. I'm pushing on him the same amount that he pushes back on me. And you might be saying, well, what about this device in the middle? I'll clear that up in a minute. But if this has negligible mass, it's effectively like we're just pushing as hard as we can on each other. But I can't push on him any harder than he pushes on me. As a result, if we exert the same forces on each other, what should be true about our recoils? Who's going to recoil more? He will, Miguel, right? Because he has less mass. The same amount of force, less inertia, he should have greater acceleration. So let's see if this works. So sit on there, try and get centered right above the bowl. Oh my gosh. I did lunges yesterday. My legs are so stiff. Oh, I'm gonna cramp up. Last time I did this, I fell. If you want to get up and move around so you can see, that's fine. So we're gonna hit the power. And then we're gonna go 1, 2, 3, push as hard as you can without. Yeah, okay, so we're gonna push it, and then remember, don't grab the thing, just push as hard as you can, straight back. Try not to fall over, I probably will. Ready? 1, 2, 3, Let's give her a round of applause. Too much mass. All right. So in this case, I had so much mass, I think I was telling the other guy the same. What, Luke? Oh, sorry, dude. I just got him in the. Oh. All right. You want to try one more? Oh, okay. Yeah, we got these hoverboards in here. Let's try one more. Now, remember what we did last time? Yes. So get centered on there. And then now, think about this. We got Miguel, he's going to throw this ball. Which one has more mass? Miguel, by a large portion, right? Who's going to exert larger force? Miguel on the ball or the ball on Miguel? Equal. Same. Oh, sorry. Okay, you ready? So you're going to throw it as hard as you can. And now that he's the large mass, he should recoil a negligible amount. And the ball will come flying off. Go for it. Oops.
No, I just wanted to see the demonstration.
Oh, I was wanting to see a biologist fall on their face. Let's see what you stand on here. Ready? Don't screw this up. Give the biologist a round of applause here. Hey, rotation. All right. We're not gonna. Let's give Luke a round of applause there. All right. And Dom's just sipping that coffee. All right, I hope that was a little bit fun. All right, so I want to talk about two problems that I think will help us dial this in. Remember, the action-reaction practice, if you need more of it, is on page 89, problems 514 through 520. I want to look at 520 and a half and 520 and 3/4 on page 90. So you can start working on those with your neighbor right now. 520 and a half and 520 and 3/4. Yeah, this erase is killing me. That's what I got to work with here. Right. And you guys can talk as much as you want. You can start working without me. It's gonna take me a few minutes to get caught up. Jules, if you want to circle around, you can. If you have questions, you can talk to Jules or. Oh man, this eraser's terrible. What's going on? This is off. Let's see if I can grab the eraser real quick. Something is really wrong with it. Talk as much as you want. Ask Jules questions if you want. Again, I'll catch up. I just did get a new eraser. Hopefully that one's gonna work a little better. Sorry about that. What's wrong there? Unsustainable if it stays like this. Ooh. Okay. We've got a situation here. We've got two blocks, and there's going to be a zombie that's going to push this way. We'll call this force subscript Z for the zombie, let's say. We've got two blocks. The one on the right is larger. They're pushed horizontally, level surface. I'm going to introduce some of the notation here. So between these two blocks, there's a surface. So there's a normal force. So we could draw, I guess on this case, you could imagine there's a force this way, which would be the normal force of 1 on 2. Sometimes I'm going to call this N12. All right, just take out the word on. So the second one is the object that it's acting on. Now, do you agree block 2 is going to push back on block 1? So there's going to be a normal force this way. Let's see one of these blues. going to be a normal force back this way. I'll call that normal force 2 on 1, or N21. Okay. Now, in this case, we're asked the following. If the blocks move to the right at constant speed, so let's say these blocks are moving this way, and somehow, some way, we're told acceleration is 0, right? That's constant speed. In this case, which normal force has a larger magnitude? Which one of these two is bigger? If we're moving to the right at constant speed, they should be the same, okay? So if A is equal to 0, I know that N1 on 2 should equal N2 on 1. Okay. Now, what if instead we change this and the blocks are actually accelerating to the right? If the blocks are accelerating to the right, which one is larger normal force? Is the one coming from the heavy object or the one coming from the light object? They're the same. Still the same, right? Do you agree? Every action has an equal and opposite reaction. I was trying to trick you. My apologies if I did. The point of this problem is to show you it doesn't matter if you're accelerating or not. And I want to point out something special here. Notice these are two blocks in direct contact. So when two objects are touching each other, they're going to exert the same normal force, whether they're accelerating or not. Okay? It's just a fact. Cool? Let's look at the next problem now. Now we're going to put a block in between them. 1, 3, 2. In this case, and there's a floor here, I think. Now we know between blocks 1 and 3, there's going to be a normal force of 1 on 3. And pushing backwards, whether it's accelerating or not, there's going to be normal force 3 on 1. Similarly, there's going to be a normal force of 3 on 2. And pushing back the other way is a normal force of 2 on 3. Everybody okay with the normal forces between the blocks? Now, in this problem, we've got this M1 still 1, M2 still 2 kilograms, and M3 is 3 kilograms. And now in this problem, the first part, part A says, if the acceleration is 0, and we're comparing which two normal forces? We're comparing N1 on 3 and N2 on 3. So now we're comparing the two normal forces that are acting on block 3. If acceleration is 0, which one of those is bigger?
Should be the same.
They should be the same. Think about it. If acceleration is 0, should the lefts and the rights balance? Okay? In fact, I could write sum of forces horizontally equals mass times a sub x. And notice the sum of forces has to equal 0. So that says N1, whoops. Oh my gosh, this is gonna be a long day. Okay. All right, fine. However, part B says if A is greater than 0, which force is going to be bigger? Or are they the same? What do you think? Again, comparing 1,3 to 2,3. Which one should be bigger if the acceleration is to the right?
Neither.
Why do you say neither? What's your logic?
I mean, they're all, as long as they're touching, they should always be the same, right?
Keep in mind, are these action-reaction pairs?
Oh.
They're acting on a single object. Can they be action-reaction pairs? No. Action-reaction pairs always come on different objects. You see that? So in this case, is it possible these could be dissimilar? You bet. And in fact, look at what we get. If the sum of forces in the x direction is equal to m a, and a sub x is bigger than 0, well, I could look at the sum of forces here on 3. I get n13 minus n23 equals some positive number, let's say NaX. Which one has to be bigger? N13. Think about it. If this is a positive number, the positive number on this side must be bigger. Or look at the picture. If this thing's going to accelerate that way, doesn't this force pushing that way have to be bigger? Now, why am I doing this, right? I hope you saw that it's a little bit tricky and confusing, and I was deliberately trying to confuse you. I want to show you something. All right. You can see. Let me zoom out a little bit. Let me do this. All right, let's zoom out a little bit. Now, hopefully you can see this on Zoom there. Apologies if it's a little small. That's pretty close to max that I can get. All right, so notice the key difference between these two problems. In this problem, we're talking about two blocks that are in direct contact, and we're talking about the forces on one and on two different objects. Whereas over here, we're looking at the forces on a third block that's in between them. Notice over here, our rationale was Newton's third law, right? Action, reaction are equal and opposite, whether you're accelerating or not. In this case, notice we're talking about the forces on a single object. I'm using Newton's second law, F equals ma. You see the subtle difference there? So that's it. I don't know. Any questions about that? I'm trying to emphasize the difference between when you should apply Newton's second law, when we're talking about two forces acting on a single object, versus Newton's third law, comparing forces acting on different objects that happen to be action-reaction pair. Good enough? So now you know kind of the ways I might try to trip you up. Now I want you to think back when we were doing the demonstration over there with the hovercraft and the big cardboard tube. Which of these examples looks most like that? This one. So strictly speaking, that was not the best Newton's third law. However, because the mass of 3 is so small, this is effectively 0 if the mass of the cardboard tube was small, because mass 3 was really small. I should be clear here. I'm talking about the sum of forces on object 3, so I should be using mass 3 here. So again, when Miguel and I were sitting over there, if we had that cardboard tube between us that had basically 0 mass, the forces were effectively equal and opposite there. However, when Miguel was throwing the medicine ball, this is a classic, perfect example of Newton's third law. So, right, You can think of Miguel as object 2 with this large mass and the medicine ball with light mass. They exert equal and opposite forces, whether they're accelerating or not. Cool? Fundamental. All right. All right. Maybe we'll pick that up later. I want to look at page 91, systems. So take a look at the top of page 91, or just before question 5.25, there should be a blurb that says something about systems and internal external forces, okay? Systems and internal external forces, that's our next piece. Gonna start erasing. A little better. That's a lot better. And you can talk as much as you want. All right. There's a cool trick we're going to learn using systems. So related to that is this concept of internal versus external forces. Okay, so that's what we want to talk about next. And maybe I'll start with a simple example, pretty similar to what we just did. So we have two blocks. So we're going to push this way with some force, capital F. Let's assume friction is negligible for this problem. Okay. All right, so if we have friction negligible here, we're pushing this block to the right, or this combination of blocks. We've got mass 1, we've got mass 2, and for a large number of problems, we want to get used to labeling the masses with subscripts. Okay? If friction is negligible and you push to the right on this, what do you think will happen to these blocks? Will it accelerate or not? If you have negligible friction and you're pushing to the right, do you think it will stay at rest? Do you think it will move with constant velocity, or do you think it will accelerate to the right?
Does it depend on how hard you're pressing?
No. Imagine, right? There's negligible friction, right? Let's say in a perfect world, there's zero friction. Somebody's sitting there on ice skates, or you've got somebody standing on a bunch of ball bearings, right? You push on them, what should happen?
It should start accelerating because there's nothing to oppose it.
There's nothing to oppose it. So in the real world, friction is never completely negligible. And that's what's weird about this. If you think about this as being like on an air hockey table, right? Even the slightest push is going to get something moving. Cool? And so what's absurd about this is, right, this is never really true in the real world. Like you can think about pushing on a car. Friction's probably somewhat negligible, right? But even if you push on a car on level ground, it's hard to get it to accelerate much, but you can do it, right? In certain circumstances. So anyways, more on that later. Side note, on those two previous problems that I was working on, I don't know if you noticed, I didn't talk about friction that much. because friction is probably realistically involved in those previous two problems. So if you want to learn more about that, wait till the next chapter. So the goal of those last two problems was achieved. That's why I deliberately ignored any conversation about friction. Friction had to be in those last problems for them to make sense. Whatever. All right. In this case, we're going to assume these blocks are going to accelerate the rate. Right? I'm using a standard XY. I don't know if you noticed in the solutions for this chapter, I try to use the coordinate system in red just so you can see it, the acceleration in red. Try to do that. Okay, I'm going to try and draw an FPD for mass 1. Because we have two objects here, it's important that we start labeling our FPDs. And just in case this is going to make it hard for you to see, I'll lay this down for a second. No, you're good. What's one force that acts on object 1? Give me a force acting on object 1.
Gravity.
Okay. What do we usually give that symbol? How do we write the force for that?
Dominant.
Oh, that's true. Wait, I'm going to start using mg. And in this case, which m do I need to use for object 1?
M1.
M1. So I know this seems silly, but if you want to make your solutions understandable on test day, test 2 now, you got to start using subscripts religiously, all right? What's another force acting on object 1?
M2 on 1.
Yeah. Oh, I heard two things. In here, I heard normal force on 1, and then what did I hear? Was that you, Maria? What did you say?
Yeah, M2 on 1.
Yes. Which way is N2 on 1?
The same as normal.
I heard to the left, but that was from somebody in here. You agree if 1 pushes on 2 to the right with a normal force, 2 pushes on 1 to the left with a normal force. Newton's third law. What holds block 1 up? Why doesn't it fall into the center of the earth and burn up in a fiery lava death?
Because
Normal force. We see there's different normal forces here. We have to use subscripts. I'm going to call this one normal force 1. And maybe just for this first time, I'm going to show you it's number 1 from the floor. Now, I don't want to write floor all the time. So in my solutions, what I do is I call the normal forces from the floor on block 1. That's the one normal force that I only use a single subscript. Does that make any sense? This is just to help you understand my solutions. So if I have a normal force between two blocks, I use 2 subscripts. If I have a normal force on a single block, I use, from the floor on a block, then I will use just 1 subscript. That's just to keep it straight. Are there any other forces acting on 1?
Force to the right.
Yeah, F. Good. Now keep in mind, what I have drawn here, let's remember in a free body diagram, this is the magnitude, that is the direction. This is the magnitude, that is, etc. This is the magnitude of the weight, and we know the direction is negative j hat. So far, so good? So together, the magnitude and the arrow gives you a vector. Good? All right, let's do an FPD on mass 2. What is one of the forces acting on mass 2? Normal force, M2G. M2G. What do you think I'm going to call this upwards normal force for object 2? And subscript 2? What else? Is capital F acting on block 2? No, the zombie does not touch block 2. Now, to be clear, if there was no zombie force, right, block 2 wouldn't move, but force F is acting on object 1 only. The zombie touches block 1. So what pushes block 2 forwards? Normal force, what?
2. 1, 2.
Now help me out. which normal force is bigger, 2-1 or 1-2?
They're both the same.
The same. So sometimes when I'm doing these problems, I get hella lazy and I say, screw it. I'm just gonna write them both as 2-1. Do you agree? Why is that okay? This is not the normal force. This is the normal force magnitude. That's the direction. It's the same magnitude, opposite direction. Now, for this particular problem, I might leave it as N12 because we're beginning, but I want to point out we could use N12 for both of them or N21. Is everybody okay with that? This is crucial because I use this in the solutions all the time. Okay, what's the force that's pushing back on object 2? What force pushes to the left on object 2? Nothing. Good. I was trying to trick you. Nice job. It's okay sometimes if there's no force to the left. It's a very common situation. Now, I want to get spicy here. I choose to make a mega block. We could group 1 and 2 together and make an FBD of the 1 and 2 system. This is what I mean by a system. Okay? I'm going to group these 2 blocks together. When I do that, I'm just going to draw that here. What is one force that acts on the 2-block system?
Gravity.
Gravity. Is it M1G or is it M2G?
And 1 plus 2.
It's both of them because it's the 1, 2. Oh my gosh, so sneaky. So we need the total mass times G to get the weight force. Okay. What's another force acting on it? What keeps it from falling to fiery death in the magma of the Earth's core? A normal force upwards. Now, to be clear, we've already used N1. We've already used N2, 1 when we used 1, right? This is the special normal force on the system where I just call it N with no subscripts. So the system normal force upwards from the floor is the one that I choose to give 0 subscripts. Now, I wish there was a better way that wasn't so complicated, but this is just the pattern that I use. I just want you to be able to understand my solution. So that's why I'm going over this. This is the pattern I use in all of the solutions so you can understand it. Is everybody okay with that? Again, 1, 2 for between, 1 for floor on this one, and no subscript for normal force from the floor upwards on a system. All right. Any other forces? F. The zombie is pushing on one of the objects in the system, therefore it's pushing on the system. Got it? What about the normal force between 1 and 2? What's that? I heard, yeah, what were you saying, Maria?
It's Kiana, but I said there's no
Oh,
more.
sorry about that. Yeah. Go ahead.
I said there was no more normal force.
Yeah, yeah. And so here, yeah, you're right. This one should cancel that one. They exist in there, but they're going to basically balance out. This is called an internal force. Oh my gosh. It's a force that is internal to the 1-2 system. Notice these internal forces will always come in action-reaction pairs and cancel out in the system. So now you know why I spent so much time doing action-reaction. What are the pros and cons of these different FBDs? Well, let me ask you something. Which one is easiest to determine the block's acceleration? Would it be FBD1, FBD2, or the FBD of the system? Which FBD helps us get acceleration most rapidly? The system. What's sum of forces in the X for the system?
Force. Oh, nice.
Yeah, what's the only force in the x direction on the system?
Force of the zombie.
Yeah. And then we got, what's the mass I should use? I have to use the total mass. And then the acceleration to the right would be a. Do you agree? It's pretty darn easy to get the acceleration of a system from the system FPD. Okay. What is valuable then about 1 and 2? What can we learn about on FPD 1 or 2 that we cannot learn about on the 1-2 system? The internal normal forces, yes. So while this isn't always true, a classic physics technique is use a system FPD if applicable. It's not always applicable, but if you can use it and learn about an equation that relates acceleration to some force. If you know the acceleration, you can get the force. If you know the force, you can get the acceleration. Great. Afterwards, you could use that acceleration in these force equations to learn about N12. Tell me, which diagram, FPD1 or FPD2, makes it easiest to determine the internal normal force N12? Which FPD looks easier to work with, 1 or 2? 2. What's the sum of forces in the X for mass 2? Give it to me. What's the sum of forces in the horizontal direction?
Normal force 1, 2.
Yeah, whoops, wrong color. That's it. Now, do you agree? If we know the force, we could get the A, we can plug that in here and get the boom. So very oftentimes, you only need 2 FPDs, even though we could probably draw 3 sometimes, all right? So on test day, a lot of times, I mean, pretty much every physics 1 test I've ever given has at least one problem with 2 blocks on it, and you have to deal with internal forces. Sometimes the system is useful and it can speed the problems up. So far, so good? Okay, useful.
This isn't on the first test, right?
This is on the second test, yes. First test is only chapters 1 through 4. We're in chapter 5 now. On that, a side note on that is, keep in mind, right after you finish test 1, you got to basically get back on the homework for chapter 5, right? Another side note, I should mention this. A common thing students do is they think, oh, I'm going to focus all my attention on physics this week, and then I'm going to ignore my Math 184 class. That's a terrible idea. What happens is you start leapfrogging, and then next thing you know, you just suck at everything. So I highly recommend you should be staying up on all your homework. Right, Dom?
Yes.
It's just, we see it all the time. People like, oh, I'm just going to focus on physics now, right? It just, you see their grade just. So you've got to keep up with all of your homework all of the time. And that way, yeah, and you've got to make a schedule for yourself. If you haven't figured that out, hopefully this semester will teach you that. All right, should we keep going? I think you guys could do the rest of the questions on page 91 at home. We could try and pick those up if we have extra time. But there's more questions on that page that force you to just write down the FPDs with these blocks, with these systems. And notice like 5.27 is a trickier one. There's 3 blocks. 5.25 looks really scary, but keep in mind, all it's asking about, it's not asking you to do the FPDs. It's just asking you to figure out which blocks or which forces are internal versus external. And I guess I should mention that here. Forces that are not internal are external. I know that's maybe obvious, but I should make that explicit, right? So the forces that are internal to the diagram, right, they're the internal forces, the others are considered external. Everybody cool with that? Now, I want to talk about a pulley system, all right? We're doing good, and I'm going to go, we'll do the pulley problem, and then we'll take a break. So let's look at 5.28. For me, it's on page 92. All right. And if it helps, I've got an example of such a pulley system right over here. It turns out you're like right in the way, but you just scoot to the side for just a second. Probably not. Oh, you're still right in the way. Yeah, I might need to just like walk it somewhere for a second. Sorry about that. I appreciate you being flexible like that. There we go. That's good. Okay, so here's the pulley system right here. Look, we've got these two pulleys. I've got two scales. And the idea is I can hang some masses on here and we can see what the scales read. Now, again, I want to remind you that when we're doing this in the real world, we know our numbers are going to get screwed up because the scales have mass too. So when we do this, keep in mind, if we run this experiment in a minute, we expect the numbers to be off from reality because of the mass of the scale. But if I use somewhat large masses, hopefully the errors aren't too bad. Hopefully they're within 10, 15%. But we're expecting probably about 50% error when we read these scales. Okay, go ahead and grab your seat, Ian. Thanks. All right, let's go to board 6. Right? So I'm going to draw this one like this. Mass 1 is initially on the ground. There's a scale here. There's some sort of weird contraption. This particular device is known as an Atwood's machine. Okay? That's not important. Names, whatever. Some people like names, I just don't care. Another scale here. And there's a hanging mass 2. All right. Now I know almost everybody in here has done this in high school or in 110, but there's still a few things that I think are worth mentioning, especially because it may have been a while. In particular, I'm going to say this is how I like to do the problem. I'm going to say this is the x direction, this is the y direction. And let's assume for right now yeah, you can tell somebody's done this in high school, huh? Let's assume for now that M2 is greater than M1. Do you agree that object 1 should get lifted up and 2 should fall down? So I'm going to label this acceleration 1. Now, just do me a favor and watch my hand for a second. Everybody just give me your eyes here. Ready? This is my coordinate system. Check this out. I'm going to follow the straight. Notice if I was taller, my hand would flip over like this, right? And so on this side, I'm going to say y is down and x is this way. You don't have to do this, but I recommend it for 2 reasons. 1, it's going to reduce minus sign errors, I hope. How about 3 reasons? 2, I do this all the time in the solutions. And 3, this is foreshadowing circular motion. You can imagine objects moving in a circle with a rotating coordinate system. So if we want to handle chapter 6 with coordinate systems that can rotate while an object spins, we need to understand how to rotate coordinate systems on simpler systems. All right. Notice, students have the tendency to write F equals ma. Well, now I know you're not going to screw up the minus sign on the acceleration because the coordinate system and a are lined up in both cases. That's why I like to do that. All right. This scale is going to read tension 1. This scale is going to read tension 2. We're going to assume the scales are negligible. What else are we going to assume? the pulleys are massless. Whoops. And negligible axle friction. So basically, we're assuming we have light, low friction pulleys. Okay. What else are we going to assume? String is massless and inextensible. I spelled that right. If I screwed it up, oh well. All right. Said another way, this is called an ideal string. Light, not stretchy. So basically, I'm not using a heavy bungee cord. I'm not using a chain. I'm using a light string that doesn't stretch that much. So these are pretty huge assumptions. There's a lot in there. There's 4 of them there. Okay. Now, I'm not going to deliberate on these all the time, but for this first problem, I think it's crucial that we understand why physicists bring up these words. In particular, when you get to this guy's class in the back, some of these assumptions may not be true, and then you'll need to know which things change approximately. So this is why I want to talk about it. Okay. We're going to assume for A1 to equal A2, what has to be true? Now, in particular, you might be saying, well, wait a minute, they can't be equal, they're opposite. No. Look carefully. What did I write here? What does this symbol mean?
Acceleration.
No. Acceleration magnitude. Do you agree it's okay for them to have the same acceleration magnitudes, but they don't have the same accelerations? See the difference there? The magnitude is how much it's accelerating. The directions are opposite. Okay. If we want A1 to equal A2, which of these assumptions tells us that that's okay? Do you know? Maybe if I give you a hint.
The mass of the scale.
What's that?
The mass of the scale.
No, it's not the mass of the scales. Let's try another one. Think about this. They're moving the same amount. Okay. Oh,
This string.
it's this. Think about this. If you had a bungee cord, right? One side could stretch more than the other, and they might not be going the same. So this has to do with inextensible string. That's the key word that tells, if you had a stretchy string, this may not be true. One side could stretch more than the other. Got it? All right, part B. What is part B? The acceleration is supposed to be constant in this problem. Which of the assumptions helps us figure that out? Sorry, this is inextensible string. Which one of these assumptions over here helps us figure out that the acceleration should be constant? No, you can have constant acceleration with friction. Nope.
This string. Oh, negligible axle friction.
No. String again.
Oh.
So think about this. If the pulleys have mass, chapter 10, I'll teach you that, but we'll learn even if the pulleys have mass, you can still have constant acceleration. Think about this if you use a heavy frickin' chain. As some of the chain goes from this side to that side, wouldn't the acceleration start to pick up? So here, the most important part is probably the ideal string. In particular, The one that worries me the most is massless or light. So if you have a, right, and again, we're on the test questions, I'm not gonna make you say this stuff. I'm just trying to help us understand why these assumptions are here, okay? On a test question, we're always going to assume this crap. Okay, in particular, these two. We're gonna use ideal pulleys all the time and ideal strings because you can handle the non-ideal cases in his class. All right, what's part C? I'm going to claim that the tension in cable 1 should equal the tension in cable 2, right? Or that these two, let me rephrase, these two scale readings are the same, right? Which of the assumptions allows us to show that is true? Do you know? It's not the string. Take a guess. No. The pulleys. In chapter 10, we will learn. Think about this. If your pulley has mass, you can have more tension on one side of the pulley than the other, which is necessary to make it rotate. So if your pulley has mass, then you can have dissimilar tensions. So I'll say here, ideal pulleys. I thought you might find that interesting. Maybe it doesn't matter to most of you, but if you're a mechanical engineer, this probably matters, okay? And to be clear, physicists are a lazy bunch. Okay? In particular, we don't want to say all this stuff sometimes. So we'll just say no mass, no friction, even though in the real world, you know everything has mass and everything has friction. But oftentimes we'll just say ignore friction, ignore the mass of the pulleys. Okay? Assume the string is ideal. Everybody cool with the assumptions? I don't know. Dom, do you ever talk about this in your classes or not? It shows up again, so if you're a mechanical engineer, you'll see it then. More on that in his class. All right. So at this point, right, I know you're getting tired, we're almost there. I want to point out that because of these assumptions, I want to simplify the diagram. I can assume that the acceleration magnitudes are the same and the tension magnitudes are the same. Okay? That means fewer subscripts to deal with. Everybody okay with that? Okay, so what I want you to do now is draw your free body diagram for block 1 and block 2 separately. I'm going to erase this and do this right here. So again, draw FBDs for 1 and 2 now that we've discussed our assumptions. New black marker. Killing me today. Let's see how they do, Jules. Let's do a loop and see if they're doing all right. Remember, you got the solution, but give it a shot first. Talk as much as you want. What's holding up the block here? Is it normal force? Remember those subscripts. Good job, people. I like that. Feel free to talk to us as we're circling. I don't even know what we're trying to do here. If you finish, just keep working on some of this problem here. In particular, part E, try to get the acceleration, and part F. So we'll try to go at least through parts E and F. Voice of good. Okay.
Remember to draw those accelerations in the coordinate systems next to your FPD, so you get in that habit.
Getting a lot of stickers here, man. Mass, it just keeps accruing. Oh, nice, nice. That's pretty fun. Make this progress. Yeah, all right, yeah.
Again, try to get the force equations and work your way down to solving for A and even solving for the tension, okay?
The good old days, eh, Jules? Easy stuff, huh? What do you think? Making progress? We call it T in this case because we said the tensions are the same, right? That was the point of all that nonsense that they had. Do you agree in this case, we said it was okay to call it the same tension, right? That was the point of the bullets here. That's right, because there's nothing in the X, so you only need to do forces in the Y.
Nice.
You've had a second to look at it. Let me pick your brains. Is everybody okay with FBD1 and the force equation 1? Take a second to look at it. You got tension up, M1 G down. Remember that one subscript matters because we got two different blocks. Tension up minus mg down equals ma up. Good to go. And notice, I got to remember this is M1. Just get in that habit. Always just be thinking about those subscripts. What's the force equation for object 2? M2G is the positive. Nice, you caught it. T is MA is positive or negative? Positive. What did I forget? Subscript 2. Now, check this out. There's lots of ways to do this. This is one of the reasons I use this rotated coordinate system all the time. Check this out. What is the internal force to the 1-2 system effectively? Tension. If you stack and add the equations, watch what happens. There's lots of things. You could solve algebraically for T, plug in, blah, blah, blah. But if you get in this habit, I want you to notice something that helps me check my work when I'm doing these solutions. When we use a rotated coordinate system, then stack the equations and add them,
What drops out? The internal force, T, yeah. So notice I get M2G minus M1G equals, what do I get on the other side?
M1 plus M2A.
System mass, M1 plus M2, times A. And I'll know I'm doing this right if I get a pop, right? Notice the internal forces drop out, I get the total mass times A. If you don't see that, you probably flipped a minus sign. The most common place to flip a minus sign is right here, because we get in the habit of writing ups minus downs. What do you think? Do you agree the A is pretty quick to get? What do you get for A?
G of M2 minus M1 over M1.
Notice the acceleration is, generally speaking, inversely proportional to total mass. Right? Now, wait a minute. How can we check this answer? Shouldn't we check this? What's one way to check it? Units. What are the units of this? What are the units of that? So what happens? Agreed? The units check out. G has units of acceleration. What's another way? What was our initial assumption about M2 relative to M1? It was bigger. Didn't we say this should be a positive number if 2 is bigger than 1? Is that true?
Yeah.
Yeah, if 2 is bigger than 1, A is positive. Yes! Wait, there's more. What if 2 is less than 1? What would happen in our picture here? If 2 is less than 1, what should happen? What do we get? Negative value. What's another way we could check this? What if you put a piano on one side and a bean burrito from Taco Bell on the other side? If you had a piano would have a large mass, right? Let's assume, we could say this in physics speak, if M2 is much, much bigger than M1, if you put a piano on one side and a flea on the other side, what should the acceleration probably be? How big? I would gonna say G big, right? Think about it. Let's check. It would be basically in free fall because the bean burrito or the flea would not hold back the piano. So if M2 is really big, and M1 is really small, you agree the M1 doesn't matter much? And what do we get? Oh, there we go. Makes sense. Now, I know this seems a little bit odd, but part of the reason we do this problem in every class is there's lots of ways to think about your answer. In fact, would we get the same answer if M1 was much, much bigger than M2? If M1 was much, much bigger, do we get the same answer? No. What do we get?
Negative.
Negative G. Then the sign makes sense. All right. Anyways, so far so good on this. Let's take that break now. All right, take that break. You earned that one. You can solve for the tension really easily by just taking this A and plugging it in and solving for C. I'll let you do that on your own. You can do the rest of the problem at home. Oh, that was a long session there. Good work.
Maybe.
Yeah, yeah. I mean, I grew up in downstate Illinois and the humidity there is bad. It's like 90 and 90% all summer long. And you know, you just, yeah, I used to run in the middle of the night, just like at 4 and it's so hot out. Yeah, yeah. I'm a strange person though. I used to do general relativity and jogging at like 3 a.m. So that tells you what's wrong with me right there.
How did that go?
I learned something, so that's cool. All right, let's get back into it. So my goal is to finish chapter 5 today, right? That way you can get started on that homework right after your test on Monday. Just before I forget, don't forget tomorrow in lab. Where's the Zoom camera? Let me get me on the right. Don't forget in lab tomorrow, we're just doing practice exams all day. Ideally, the best way to do it is to come in with some questions. And don't forget, when you're taking practice exams, take them like a real exam. Time yourself, use a calculator, don't use the solutions, then grade yourself. And if you don't understand the solutions, that's what I'm here for. So if you can have a test taken before you come to class, that would be great. Also keep in mind, tomorrow it's okay to come in on Zoom if you want, right? Because we're just doing it. So we can be answering questions over Zoom pretty effectively there. So just letting you know what lab is tomorrow. Everybody got that? And that's kind of like payback for all the hard work you did on those talks. Thumbs up for you. Okay, great. I want to talk a little bit about some kind of advanced topics. And in particular, I want to look at this situation right here, and I want to look at page 96 in your workbook, problem 5.41. 5.41, and let me see if I can get this on the Zoom camera while I was sitting in the background. Oops, wrong way. Give me just a little bit there. And then I think you're going to be right in the way. And I appreciate everybody in class. I hope those of you on I hope those of you on Zoom appreciate what all these students in here are doing as they move around and deal with me clicking on this stupid stuff.
It's okay. Physics fun.
That's right. That's right. So, hey, class, let's give yourselves a round of applause for dealing with this crap. All right, very good. Okay, so I hope you can see this in front of you pretty well. The idea is, whoops. Really some black string. Yeah, that would have been good. I didn't think about that. Well, let's just take this off.
Or flip it.
Yeah, let's get that McDonald's. So
Let's go.
we're gonna get the McDonald's one. Does that help?
Yeah, it's right there.
All right, all right. Thanks for the advice. I appreciate that. Go McDonald's. McDonald's hooks us up with straws, but we need to
Free
build stuff.
advertisement.
Yeah, right. So they helped us out at the science show and they gave us all, I'm like, man, I really need some X, Y, and Z. And it turned out I needed this one here. They gave it to us. So hey, thanks to them. Anyways, take a look at this weird contraption. We've got a brick here that's holding this string, right? Then the string wraps around a pulley and comes back to this cart. Now, to be clear, this giant rubber stopper is keeping it from moving. But we see that you can have this thing move in just a second. Way down at this end, notice this pulley is attached to a hanging mast right here. All right. Now, hopefully, Jules, did that show up at all on Zoom? Yeah. Thanks, I appreciate it. All right. So in this case, we're starting to see an advanced application of pulleys. And so I'm curious about this particular problem. Let's draw it up on the board and get a feel for it. Okay. So let's take a look at what problem was this? 5.41. And if you look at the bottom of the page, there's a realistic picture of it. So I'm going to get back on the board here. Obviously, this is mechanical engineers bread and butter. Right, Dom? He's doing this in his class right now. So we're going to do a simplified version of this, and we're not, I'll explain more like what's on test day after we do this problem, but let's take a look at it. So a simplified model, we've got this floor here, some kind of table, some kind of wall. We've got a pulley right here. We've got a block right here. This is attached to the block. There's string coming off this way. Oh my gosh, those lunges hurt. Oh, man. I went for it and I'm just super slow right now. Another pulley over here. String's coming down. And I forget which of these are which. Which one's 1 and 2? One is this block. This is object 2. So we know what's going to happen when you let go of this thing, right? When I pull the stopper out, which way is object 2 going to go? Down. Okay. Which way is object 1 going to go? To the right. And to be clear, you may be saying, how are we oftentimes ignoring friction? Well, one of the tricks that we do in the real world is if you put tiny little wheels on the bottom of here, the friction is negligible, right? Think about dragging a suitcase around with little wheels on the bottom. The reason they do that is so that, or a dolly or whatever, right? You're trying to make friction negligible. So you put these tiny little wheels here that have negligible mass and use negligible amounts of energy. So basically, it's like putting ball bearings underneath the whole thing. Okay, great. All right, so now, suppose M2 falls distance h. So let's say this one falls down some distance h. My question is, how far will object 1 move? What does your gut tell you? Is it going to move distance h, more than h, less than h? Take a second to discuss with your neighbor. Tricky, right? It's not necessarily obvious. Help me out. How far is this pulley going to move? It's attached to the same string. We're assuming it's an ideal string. If this goes distance h, how far should the pulley move?
It's the same.
Yeah, and now I noticed my distance h is a little bit too big because I can't quite. Let me make it a little bit smaller. That's a little easier for me to draw. So do you agree? The pulley should also move distance h, right? Well, if the pulley moves distance h, how much string needs to be added to this side of this cable? You're going to have to put h on there, right? This will be the new position of the pulley. How much gets added to this side? So how much string is pulled by this brick? What? Look, I need to take h, right? This is the extra string that I have available to me, right? I need to get h of it extra here and h of it extra there. Yeah, so we should see this. Let's actually look at the object move, right? So the claim is delta x1 should equal twice h, right? It should move twice as much. Let's see if that's true, right? Let's see if I'm lying. Oops, wrong way. All right, and so I'm probably going to need, you want to just come up and help me because I'm going to need an extra human being up here. All right, so what we're going to do is, we need a meter stick. Whoops, I forgot my meter stick. Here it is. So let's do this. What I'm going to do is I want you to stand over there and just hold the cart. Take the rubber stopper out, but just hold it with your finger. Yep, take the rubber stopper out. And then kind of lean way back so they can see it like, yeah, there. Now what we're going to do is, right now, the bottom of this is at 30. So what I want you to do is just slide it toward, oh, and what is the end marker of U? It's right at what, 20? Right here.
Oh, here,
Yeah, what is that?
19.
19? Okay, so he's at, so the cart
X initial equals 19 centimeters. And for me, the hanging mass was, what did I say, 30 centimeters? I'll say Y initial, okay? Let's run it.
Give me a sec. Let me get the meter stick in the right spot because I got to compress just a tiny bit of foam. Okay, now slide it, let's say 20 centimeters. So you need to go to what, 39?
Yes.
Go to 39. Are you there?
Yes.
Can you see how much that moved? Yeah, to 40. 10 centimeters on this side, 20 centimeters on that side. Got it? Let's give him a round of applause. So notice, let's see, if this one moves H, this one moves 2H. Now think about this. At first, this seems really stupid. It's just a bunch of cables running around. Is there an application to this? Well, I'm just going to point out, you agree that X1 is basically equal to 2 times Y1, or whoops, 2 Y2, excuse me. And I'm going to stick absolute values on these here. All right. What does that tell you about the accelerations, however? Oh, whoops, thank you. Thanks for telling me on the Zoom. Sorry about that. Okay, right? Just pretend I'm using a rotated coordinate system, so I don't need to use these absolute values. So again, I'm using this coordinate system. This way is the positive direction, right? Anything that's going, what is that? Clockwise is considered positive. So in this case, what does this tell us about the accelerations? Will this block accelerate the same as that block? How do you get from X to acceleration?
You take this
Second derivative. If I take 2 derivatives of this, I'm going to get a 1. If I take 2 derivatives of this, what do I get? We see we get an acceleration multiplier as well. If the object moves twice as far, it's going to accelerate twice as fast. Cool? So this is the, I guess, the beginnings of, you could see that pulleys can be used not only to redirect force. In the last problem, we saw the pulley was used to change which way tension was applied to different blocks. But you could also use it as a force multiplier effectively. Got it? Pretty crazy. Now, let me see what else I want to do with this one. I want to do an FBD for this pulley. I want to try and understand things by drawing an FBD of the pulley itself, not the block, not this block, this pulley. You can do that. There's my pulley. We'll say there's something at the center that you can attach to, right? And I think in this particular pulley, what does it look like? I think there's like a bar right here, right? What is one force acting on that pulley?
tension,
Tension. Which tension? Which one?
both left and right.
Okay, so how about we call this one, because it's attached to block 2, can we call this tension 2? And should this be tension 1? Are you okay with that? So I got this one. There's going to be tension 2 this way, right? Anything else?
Gravity.
Okay. I'll put MPG for mass of the pulley. What else? What about the other string? If you didn't know this, the other string is being applied twice, right? So if you're not familiar with how pulleys work, this is an FBD of a pulley. In particular, this is a tension that's acting on the axle at the center of the pulley itself, but the string that wraps around the pulley is exerting a force on it. Now, here's where it gets a little bit complicated. I'm going to say something
that's going to probably confuse you, but I feel like it's important, so I want you to listen as carefully as you can. What's actually happening here is the string is coupled to the pulley using friction. Now wait, didn't I say the pulleys were frictionless? We're assuming negligible axle friction. So the axle of the pulley has no friction. Now, there's lots of friction between the string and the pulley itself. Otherwise, the string would just slip around the pulley and it would fall right around, and the pulley wouldn't twist. So we know if the pulley actually turns, there has to be friction between them. So this is a very subtle thing. There is friction between string and edge of pulley. If you're really interested in that, I could teach you about that later, but for now, I just wanted to point out that the net effect of this friction that exists between the string and the pulley, we can just cheat and say, look, the tension in the string is acting on the pulley. And really, it's acting on the pulley through the friction that exists between the string and the pulley. Is that good enough? So this is how you would draw a pulley FED. Something is wrong here. What do you notice about the forces up and down versus left and right? Well, let me ask you this. Is there any force right now that balances the mass of the pulley? No. In practice, in reality, it should probably look like this, where they're angled up slightly. You know what I'm saying?
Like how it looks in the model you have right there?
Like real life. Yes. So if you look at the model here, you could see there's a slight angle in here. Now, to be clear, if the mass of the pulley is tiny, if the mass of this pulley is tiny, what happens to this? If this is approximately equal to 0, then the angles are basically purely horizontal. So typically what we do in this is we assume the mass of the pulley is 0 so that everything can be purely horizontal. And that's pretty darn close to real life. If you look at the real life, it was really close to that, agreed? And in fact, if the angle is less than about 8 degrees, the errors are less than 1%. So it turns out you could actually have a somewhat significant mass here. As long as the angles are less than about 8 degrees, we're good. Enough on the mass of the pulley? All right. Let me get rid of this. So we're going to assume this term drops out, because it makes our life easier. So far, so good? I don't know. Well, when we do this, look what happens. Let's do the sum of forces in the x direction for the pulley. That's going to equal mass of the pulley times A. Well, what did we just say about the mass of the pulley? So what has to be true about the lefts and the rights?
They cancel out.
Yeah, so notice T2 is equal to T1. So we see that in this case, the pulley can be used to multiply the force. If you have twice the force, that's how we're able to get twice that acceleration. Cool. And again, there's more to this. Yes, question?
There's an anime called Dr. Stone which kind of shows this. And like the main character, he was trying to pick up like a tree trunk, and he uses like 3 pulleys. He like calculates all of it.
That's
like,
right. That's right. So there we're getting, actually, we'll do that one next. Okay, yeah. The green screen over there. We'll get to that in a second, right? See all the pulleys and we'll get to there. Just trust me. All right, so, okay. What was the main thing I wanted to get out of this example? Number one, if you're a mechanical engineer, you should be good at this. And you should spend a lot of time getting these FEDs right and being expert at it. Civil engineers too, basically any engineer, right? Anybody that has to take statics or dynamics needs to be a master of free body diagrams. Number two, we talked about how friction or between the string and the pulley, we could cheat and use this tension acting on the pulley in this manner. Okay. So this was kind of the thing that I really wanted to focus on, was you could draw an FPD of a pulley. Now, in the interest of time, I need to keep going, and I'll talk about this more in a second. In particular, I wanted to get to the block and tackle example over here. So the rest of this problem, just leave it aside for a minute, and I want you to look at page 97. I'm going to go this way. This one. And then I guess your head's right in the way. Sorry about that. Oh, and also you. Yeah. There you go. Thanks. Then let me do this. I would like to rotate this table just a little bit. Is that all right? Yeah. I don't want to drop your laptop. Okay. Jules, can you see the weight on the bottom? Not quite. Okay. It's not on Zoom. Yeah, there's something on the ground there. Let me. Oh, whoops! We're gonna have to move that table out of the way. Oh, yeah, that one. Can you push that one back? Just shove it into Dom's face. He loves that. Sorry, Dom. There we go. Thank you. All right. So we're looking at an example of a block and tackle. Now, in order to do this, I'm going to have to be a little bit quick with these scales because, as you notice, the scales just auto turn off. So I don't know if we're going to be able to do this very effectively because I'll have to tell you what the scales read. But you can come up here and see this. The idea here is this is an example. I'm just going to kind of bunch this up here. If I pull on here, we can read how much tension I exert on this end of the rope. Over here, we can see what the weight is of that mass on the ground. And then in this case, we can also see what the scale is on the ceiling versus this scale right here that's trying to hold this up. So notice we've got all these different scales so we can read the tensions in these different parts. So now what I need to do is turn them all on without any tension specific. All right, they're on there, so I'm going to lift these and hold them. And then can you remember all these numbers after we lift it? So I'm going to lift this thing, ready? In this case, whoops. Okay. We'll let it stabilize. You got a pencil or something? Can somebody write this down? Okay. For the weight, I've got 4.85 kilograms. 4.85 for the weight. 2.1 for what my hand is reading. 2.1 for my hand. Up there, I've got 2.1 on this one right here. 2.1 on the whatever. And then the very top one reads 705. Got all those numbers? Yeah. 4.85, 2.1, 2.1, 7 point something, whatever I said. 7.05. Okay, so let's go back and look at this on the board really quick. Hang in there. All right, we're seeing an actual application here. We saw 7.05. Now, these were all in units of kilograms, so these are not weights. But if we multiply all of them by G, do you agree we could get weights? So apologies of the funky units. This is what the scales read.
The next one is the 2 point. There's two 2.1s.
Yep.
And there's the 4.85.
Now, I know my picture isn't perfect, but I want you to think about this. These are the numbers that we just saw. And then to cheat, I'm going to multiply all of these by 10, which gets us to newtons. Are you okay with that? Right? G is approximately 10. So I'm just going to point out that this is basically 70.5 newtons, approximately. This one's approximately 21 newtons. This one's approximately 21 newtons. And this one down here is approximately 48.5 newtons.
Now let's think about this. If I look at the, oh, this is sloppy, sorry. There we go. So the idea is, look at this cable. The cable that was wrapped all the way around has the same tension throughout the entire cable, right? 21 newtons here, 21 newtons there, 21 newtons everywhere. Now, to be clear, these scales are a little bit wonky and I'm trying to pull this live and react. I just want to point out, let's look at these numbers down here and see what's up. If I look at this pulley, I've got 21 newtons up on this side, 21 newtons up on this side, because that is the same cable, right? 21 newtons here, 21 newtons here. And this is about 48 newtons down, 48.5. This is not perfect. Now, what's happening is when I have to lift this up, one of these that was probably accelerating upwards, so I probably had slightly more tension at some point. These tended to lock in at a lower tension than this one when it was reading, whatever. But do you agree these are approximately balanced in the real world? Now, we don't get something for free, right? Look, I only need 21 newtons to lift a 40 Newton object here, right? Just cheat and call this 40 and that's 20 so I can speak. What is the trade-off, right? I only need 20 newtons here to lift a 40 Newton object. What's the true cost? Why am I able to do that? What's the trade-off? What's that? Ah, let's look at the top pulley there. Okay. Now look, how many times does the 21 newtons act on the upper pulley? 3 times, right? 21, 21, 21. Blackjack. All right. And notice that's about 63, which approximately, again, this is not quite perfect. It's the real world. Okay, these scales don't always lock in on exactly the same time. And so sometimes if I'm shaking it a little bit, it'll misread this. But we see that these 3 forces approximately balance that. That's why the upper one's balanced. So again, if we do some severe rounding, 40, 60, it looks pretty good. So notice you're not getting something for free. All that weight has to be supported. You're not only supporting the weight, but you're also having to support the extra amount that I'm pulling down. So that's one cost. You put more wear and tear on the bolt that's on the ceiling. What's another cost? Friction. Okay, true. There's some friction, and that's going to also account for some weird factors into these numbers, I'm sure. What else? Tension. In particular, there's one key thing I'm looking for here. I'm just going to do it so we're not talking all day. Distance. Look at this. If I pull this side 1 meter, how much does this one go up? Half. Let's go look, right? You get twice the force, you double the force, but you only get half the distance. If you try to ever lift an engine block out of your car, give me a few more hours, right? You're pulling lots of cable, but you have a very low force. Let's go look at this thing over here one more time. Where was this? So this is the opposite of the last problem, where remember in the last problem, we, I think, got double the distance or something. In this one, we get half the distance. So depending how your pulleys are connected. Oh my gosh. All right. Whatever. Okay. So in this case, let's take a look over here. You want to just help me out? All right. So I guess what we could do is, let me do this. All right, I tell you what, I'm going to do this. I'm going to pull this thing 1 meter, right? Which means I need to go basically right down to where the top of the weight is, right about there. So I'm going to pull this thing 1 meter, which goes to about right here. That's 1 meter. And then I want you to see how much this mass goes up. I pulled this about 1 meter. How much did that move approximately? Oh, look at the bottom. Look at the bottom. Watch. So look at the bottom of this, right? And then read where the bottom is. So I need to go to about right here. How much did the bottom move approximately? 48. 48, so about 50. Agreed? All right, let's go. So again, oh, thanks. Let's give a round of applause here. Take the ball back now if you want. Oh my goodness. The point of this was this. We saw that if I pull 1 meter of rope here, the mass only goes up 50 centimeters. I get twice the force, half the distance. Man, if only there was something called a force distance trade-off that we were going to learn about in chapter 7 that would discuss this more. We'll discuss that more then. You want the good news?
We're done with chapter 5.
What's that?
We're done with chapter 5.
Well, even better than that. The questions I've just discussed, 541 and this, are not on the test. But I knew if I told you that at the beginning, you wouldn't listen. So if you're interested in this is a sign you should be a mechanical engineer. Yes.
I just had a question because when I was looking at the newtons over there and how you have 70.5 newtons pulling on the ceiling, that is roughly the force of the total of what you're pulling plus the weight of the mass. So would it not be what you're pulling down and the weight adding up to that one?
No, to be clear, this is a good question, right? The idea is when we look at a free body diagram of the pulley, here's the pulley itself. What things are actually touching the pulley, right? It's the strings. That is the only things that should be drawn on the FBD of the pulley. Well, we're assuming there's negligible mass here. There'd obviously be an mg for the pulley, but we're ignoring that. Okay. So in an ideal world, if you do this, right, the idea is, yes, this mass matters because it's connected to here, and that causes the tension in this cable. But then that tension in the cable is the same cable that's pulling on this 3 times. It's that, yeah, it's literally, if we call this T, 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 and I call this T ceiling for C, it should be TC equals 3T. It's not adding the mass of this because that's already accounted for in the tension of the cables. And the only reason the numbers don't match up is purely just error in holding this thing and shaking it while I'm trying to get the data and it freezes. That's literally all it is. So this is the story. Yeah.
Yeah, since we assume that the pulleys are massless, the only mass in the equation is that block, and that's what provides the tension, right? It's the
That's right.
resistance.
Yeah. Now what's happening here is if I'm pulling this somewhat quickly to get the demo done live, what happens is it's accelerating for a split second. And to accelerate, you need more tension than the actual weight. So what probably happened is here is while I jerked this down, this one locked in while it was accelerating upwards. And then these ones locked in after I stopped wiggling it. So that's why this one's reading a higher number than those. And this one probably locked in while it was accelerating upwards as well. So keep in mind, if this block is accelerating upwards, we should expect the tension in that scale would be greater than the weight to make it accelerate upwards. Is that good? That's really what's happening with these numbers here. Yeah, good? All right, that's cool. So again, page 96 and 97, like 541 and 542, 543, not on the test. But if you like this kind of stuff, take Dom's class or become a mechanical engineer. If you don't like this stuff, I don't know. Be careful. Maybe you shouldn't be a mechanical engineer. But it's pretty interesting, right? It's reality. All right. Oh my gosh, what a crazy day. I got a question for you. Look at problem 5.21 on page 90. Let me get this over. 5.21, page 90. And then I guess we're right here. Yeah. Sorry. We're going to do a couple of these. You may want to just flip seats over there. Sorry about that. All right. We've got some weird looking fan cards here. And could you do me a favor and just be at the other end so I don't accidentally crash off the end? Jules, are we kind of in the frame? All right. So now here's a fan cart. Nothing fancy here. I don't know if you can see this. The air is going to be pushed this way. So I'm going to turn this fan cart on. Where's the on button? There it is. Goes that way. Go ahead and check. Try not to chop your fingers off. Go ahead and turn that off. Hand it back into the middle. Switch it. Yeah, perfect. Thank you. All right. This is exactly what we expect. Now let's think about this. What is the force that makes the cart go towards him? Okay, air resistance. What do you mean?
The blades pressing on the air, which causes it to go.
Okay, the blades pushing on the air is a force on the air. By Newton's third law, what is it? What pushes
The air.
the air pushes the cart this way, right? The cart pushes the air this way. By Newton's third law, the air pushes the cart that way. Okay, fine. Now, I've got this screen right here. I'm going to put this on here. Then I'm going to turn it on. Which way will the cart move? Discuss with your neighbor. You can just talk to them right there. I'm going to get an MPD reading.
I feel like one was that thing. I saw. I can't explain it. It's not all the way. I guess like there's
So the air that presses back.
that's what I'm thinking too.
It moves air. It's gonna smell it. Presses on it. That makes it stress. It's pressing on it.
That's all. Unless it's just on the book. Like a sail, you know what I mean? Like a boost.
Okay, just go step over there for a sec while I do the board. Thanks. You're good. So, all right, which way do you think this cart's gonna move? In this particular case, the fan is pushing the air to the right. Okay. Which way does the air push on the fan? Okay. Now what's going to happen when I put that giant sail and basically block it?
The air presses on the sail.
Yeah, so which way does the sail push on the air? So based off that, which way does the air push on the sail? Let's see, wait a minute, am I screwing this up?
Yeah.
Okay, hold on, I flipped something. Okay, so the air is gonna move, oh, which way? Oh, whoops, I think my fan is backwards. I pushed it back. Whoops, the air is, okay. Oh, so my sail's on the other side. I apologize. This did not match my demo. I was looking at this and the board at the same time and I screwed up. You agreed. We'll show this demo in just a second. Sorry about that. The sail is over here. All right, all right. And then which way is the airflow going? Sorry. So, I screwed up everything. Oh my gosh. I screwed up everything. Let's start over. Okay, so the fan's pushing the air this way. Sorry about that. Fan pushes the air this way. So then the air will push on the fan that way. That we agree. All right. That's what we saw when we had no sail on that. So now with the sail, right? Which way is the sail going to push on the air? Right? So right, think about this. The air is going to be flowing this way. And as a result, the sail is going to push this way on the air. So which way does the air push on the sail? Sorry about that. Now, because we have the fan pushing one way, being pushed one way, but the sail being pushed the other way, what should be the net motion? Let's see. All right. Whoops. Gosh. Oh, the good old days. Okay, you ready? Sorry, it takes so long to do this. So in this case, Now, we notice there is a slight motion here. Do you agree? If I could get this fan even closer, or the sail even closer, and let go of it here. If it's perfectly centered, we should see a negligible amount of motion, but compared to this before. It's clearly a lot more motion when we don't have the sail than when we do have the sail. All right, so finally, last one, this is a screwball. I like this one.
Turbo. Supercharged.
What's that? Yeah, you can just throw that outside. We'll smash it like, oh, look at this. I wonder if this table's not level. Did you see that? That may have been why this thing was slowly drifting that way. Anyways, I should have leveled this table and I didn't think about that. But now when I do this weirdo contraption, the fan is going to blow air this way. Which way should this cart move if the fan is blowing air into this weird tube? Go ahead and discuss. I'll try and get it drawn up. I'm going to actually look at the picture before I draw it this time. This time we've got the sail. Air is going to be pushed. Oh, whoops, we want to do it this way so it matches. All right. So now the fan's blowing the same way as every other experiment. Okay, so the fan's going to push the air this way. We've got this contraption here. All right, let's talk about it. So again, the fan, which way is the fan pushing the air? Just making sure the fan's pushing the air that way, into the tube. So the fan pushes air that way. Right? So which way does the air push on the cart? Opposite. Air on fan. That's that force. Now the air is going to be moving through here. And come out the other side. Which way does the tube push on the air?
To the left.
So which way does the air push on the tube? Okay, so do you agree the air? Right? The wind was going this way. The tube forced the air that way. So the tube clearly pushes on the air that way. So now which way should the cart move? Right, left, or stay at rest? What do you think? Which one of these forces will win, or is it going to be a tie?
Tie?
Okay, let's go take a look at it. It gets tricky, right? Oh my gosh. Last one of these, I swear. I think this is interesting though. All right. Let's do this so you can actually see it. Okay, so in this case, put this right here. Is that what you thought? Do you agree it's clearly moving quite easily? So why is that? Let's look at the FBD. You can learn a lot by looking at an FBD. That's what I'm trying to teach you here. I don't know if that's getting through. Oh my gosh. In this case, do you agree the cart went this way? The cart was accelerating that way. Which force has to be bigger then? Air on the tube or air on the fan? Which one had to be bigger if the cart is accelerating that way? Air on the tube. Think about it like this. This force got the air moving. This other force not only had to stop it, but had to reverse its direction. It's going to be approximately twice as big, right? This one brought the air from rest up to some speed. This one brought it from that speed to the same speed the other direction. You get twice as much force when you reverse the direction of a particle. We'll discuss that more in chapter 9. But I just thought this was somewhat interesting. I don't know. Cool with that? Hopefully you found that slightly interesting. One more. Oh my gosh. Thanks, McDonald's. All right. I've got this weirdo looking demo here. Let me show you right here. Look at problem 5.13 at the bottom of page 86. 5.13. I'll get there on the Zoom camera. Last one. And then, oh, I'm so sorry. You gotta move it yet. I'm sorry. Probably could be smarter, but I'm not. Right? I'm just trying to hang in where my demos are located. There's probably something smarter I could do. All right. Right. So in this case, maybe I could even do that right there on your table here. I'm gonna go right there. You move that chair just a little bit out of the way. Yeah. Got this weird tube. Took a hula hoop. Actually, and then I made Angus do all the real work. I made Angus cut this hula hoop. So the idea here, I've got a marble. So I'm going to flick this marble through the hula hoop. Now, in order to make this thing keep moving, I need to put a little tiny bit of lift on there. So I'm going to put one side slightly higher than the other, otherwise the friction will slow this thing down and it won't make it through the tube. So the idea is I'm going to flick this marble through the tube. All right. And my question is, which way will the marble go when it exits the tube on the other side? So again, I'm going to put this marble in here. I'm going to flick it. When the marble comes out, is it going to move? Is it going to go off this way? Is it going to go towards the center? Is it going to go in a straight line? Is it going to be curved? Take a look at 5.13. 5.13, there's 5 different paths, A, B, C, and D. Take a second, talk to your neighbor. Which way is it going to go?
The speed increases though. It's kind of like angular momentum.
Let's not take all day just because it's time for you to go.
It's gonna go straight.
It's okay, we like it.
Let's take a second and see. Ready? Here we go. So I'm going to flick it. I think I need to flick it really hard to make this work. Straight line. Do you agree? Did you see that? The idea is, while it's moving in a circle, there's a force that causes an acceleration. As soon as it leaves there, an object in motion stays in motion. There's no external force. Now, technically, there's no net external force. What are the external forces on the marble when it's rolling across the table? Give me one.
Friction.
Oh, okay, true. We're going to assume that's negligible. What else?
Normal force.
Normal force and mg, right? So those are the two main ones. So those cancel each other. They're not actually pairs, but again, we'll just see this rolls in a straight line and then you can go away. Definitely rolls in a straight line, right? All right. So just remember that. We'll discuss this more in chapter 6. I hope you had a good day. Oh my gosh, that was intense.
But the friction wasn't negligible. The rotation of the ball could change.
You can have spin, right? So yeah, you can, like, if you've ever done that where you take a ball and you
Like
can
a
do that.
basketball.
Yeah, or you can just kind of, so spin is different. That'll change things. Or English on a pool ball, right? These are spells and stuff. So absolutely, we're doing a simplified case there. All right, you guys have a great day. If you have questions, I'm available. Tomorrow we could do, and don't forget, on Friday, I'm also extra office hours in the STEM Center too. So we got 2 days in a row. I want you to succeed on this first test. We're doing as much as we can to help you.
What about Saturday?
No, not on Saturday. All right.
I thought you were doing extra.
All right. Hopefully get you off to a good start with your first test. Hope that's the goal. Oh my gosh. Man. All these remotes.